I think probably the way we're going to talk about this today is going to be the most fun way we're ever going to talk about this again, because it's the introduction to dynamic programming. And we're going to get technical, as we always do, as we pass through the subject, so this is probably the most fun lecture on the subject of dynamic programming. So, the pack is thinning a little bit as we go on, but that's okay. So, does anybody want to tell me, what dynamic programming is? I'm sure there's some sort of, like, there's a very technical definition somewhere that, you know, someone probably might have memorized. Does anybody have you looked it up, or do you know in principle what it's about? So?
You take out big problems, break down some problems, find solutions to solve problems, put it all back together.
Yeah. So okay, so it involves this notion of breaking problems down. But why is that an advantage? Like, why is that different than, say, something like divide and conquer, where you just split something into two pieces? Or what's the big characteristic? When we think about dynamic programming, why is it a little bit more important than that? Yeah. So the key idea is that these subproblems. So if you have subproblems generally overlap. And why does it matter that the subproblems overlap? Like, why wouldn't you just use like a recursive algorithm in these cases? And this is the kind of the eureka moment.
Because we may be able to reuse intermediate results.
Going to reuse intermediate information. So the general idea, and so that's why I think dynamic programming, if you look up where the name dynamic programming came from, it's kind of funny. It was just made up. Like, it doesn't necessarily have anything to do with the underlying approach. And I think it's actually kind of the opposite, because it's really about static programming. It's really the opposite. Dynamic programming is really writing a recursive algorithm and having it do everything dynamically. Whereas in dynamic programming, the reason it might be confusing to think about it at first is because it's actually the opposite. It's really more like static programming. The general idea is we're going to find a way to form or to build upon a static structure of some kind that allows us to get a problem or a solution faster because we're reusing information. So that's the general idea going forward. So yeah, so that's what we're going to talk about. Yeah, so there are your readings and stuff. I'm going to start writing. So the general idea is that, yeah, we use static values to simplify repetitive operations. I'm going to give you a real life example because this just happened to me last month. So I had the opportunity, the studio had an opportunity to work on a really cool project about a month and a half ago, and then we signed an NDA, so I can't talk about too much detail, but what I can talk about is the idea that it was a fundraising platform for a really notable Canadian charity, which was really awesome. And so we worked on this problem. We were brought in as contractors because this donation system was broken. And so in this situation, there was kind of like there was a simple goal. So the idea is that we wanted to generate a leaderboard. So given there's a bunch of donors, so say donor number 1, donor number 2, all the way down to donor number 100. They were teams actually, and the general idea was that the person in category 1 raised like say like $15,000 or whatever, and the second team raised $3,000. And then after that, everyone raised like 500 or whatever, because no one else really did that much fundraising. And then all the way up, and then you have their names. Does anybody know UML? Is that a thing? Did you guys learn Unified Modeling Language? Cool, I love it. Use UML all the time, it makes your life very simpler. So, unfortunately, not a lot of people know it, so it can be difficult in practice. But so the general idea was that they had many teams. Actually, I'll fill out this for you first. So, have many teams. Teams can have sub-teams. And all teams so all teams have members. So this is just, it's not really an important question, we're just using this to consider the sort of introduction. So the UML looks something like this. I'm just going to do a quick sketch. So if you had some fundraiser, in the fundraiser class, they'll have some sort of amount, which they're fundraising, and then a function that gets the amount. And as inheriting it is the actual team. And yeah. And the idea is that each fundraiser can have 0 or many children. And at the end of the day, people were joining and changing teams and jumping all over the place. And so that was a problem for them. So they had a difficult time with the caching system. And really, you know, given any general team, when you had the get amount method, the real thing that was killing them was that the method was implemented like this. It was something like, they just literally had this code in there. Which I guess I'm setting it up, you already know that it's not the best thing. Was something like, it was the amount, team amount, plus the sum of all, you know, children. So they kind of had this sort of thing going on. Does anybody want to tell me about that, or why it's good or bad? And it's good and bad. Like, does that make sense, what's going on? So if you have a parent item, the amount is assigned, the get amount, which is just equals, the amount of the team, so let's say T amount, plus the children's amount, and then the children, in turn, will have their amounts. So it's really inefficient. And what ends up happening in practice is that a lot of teams, when people switch teams and these amounts have to be recalculated, every time the leaderboards hit, there's people that are members of 2 teams. There's all these weird things where there's lots of overlapping subproblems. And basically, to load this page, it was a website, and to load this page, it was taking like 20, 30 seconds. For some teams, it was just crashing. So once one team got a lot of members, and then included another team where you had these team mergers happening, the website was crashing, and the developers had no idea how to fix it, and so they were spending lots and lots of money on upping server capacity. And so this is a real problem. Like, I mean, this is a team of like 10 people working on this problem. And so it's going to be guys like you going out that are going to work on problems, and so you really have to let these concepts sink in if you can, because this is rampant, this idea that recursive algorithms are awesome and that they only take a few lines of code. And sometimes your compiler will save you, and it'll convert your recursive algorithms into something that you can use that will be optimized, but most of the time you're better positioned to think about the problem for a while and come up with an iterative solution. And And so that's kind of what we're going to talk about. Yeah, so today on the menu, we're going to talk about activity scheduling again. And we're going to consider the idea of activity scheduling with profits. So I'm going to start here. So any questions about why that was so bad, or is it's pretty clear? Yeah? Okay. So, okay. So the general idea with this problem is, as always, we'll be given some input, and it's going to be the same set that we usually deal with activity selection A. Whereas the J starts at 1 and goes to some. And so this, you guys remember from last time that that's just like a long set. In this case, I don't know what the A's. Jeez. The AJ is going to equal some start time, some finish time, and we'll also, with each, we'll have an associated weight or importance. Yeah, for here, I'm going to really try to keep to the convention here that, and I'm already breaking it, that the J's are the set index. And then later when we talk about the algorithm, we'll use an algorithm index, because that's kind of like a weird, we're using double notation a lot, and it's kind of weird. So this is going to be a set index. Yeah, and I think these are pretty obvious, so I'm not going to define them explicitly. Is that setup clear? Any questions about that? So they're like, I mean, these are just numbers. They're in a set of numbers. Okay. So, would you be able to solve this with a pure greedy strategy? I mean, I'm kind of setting up it's a loaded question. Or the question would be, why can't we set this up for just a greedy strategy? Does anybody have a good reason? The general idea, if you think about it, when we're trying to solve a problem, we consider a couple sets. So let's consider this A, where we have a very large thing worth 100, and many small things. Like, is there an obvious greedy strategy that will select the 100 versus these ones? And you could say, yeah, like, we'll pick something with really high profit, or do some sort of math with the profit that makes the profit thing good, better than the other ones. Like, okay, you can consider some other set. We have a couple big ones worth 10. And maybe a few small ones worth 5. So they're a little bit more dense. But maybe they're pretty close to the... So it's hard to choose. You can't really base it... The reason it's difficult, and it should be difficult to come up with a greedy algorithm, is because greedy algorithms are usually good at maybe 2 things. Maybe you can get away with a few things. You can sort your set, then you can kick out a bunch of elements. And the idea is that when you're doing these activities, that the local thing you're doing on an element-to-element basis compared with maybe the predecessor or the next one, it's usually sufficient to get you to your optimal solution. So they call it the greedy choice property. And it's the idea, the greedy choice property is that when you're doing something locally, when you're optimizing and looking for the greedy solution, that you're automatically finding the globally optimal solution. But it's not a general case that that's true. I mean, there's lots of optimization problems where you have to consider tens or hundreds of elements of a set to start to find that sort of that structure. And so that's where when you have that problem that you can't find a greedy solution, then you have to start thinking bigger. Yeah, so I mean, if we consider other algorithms, another greedy algorithm, in this one we really had a couple things we're worried about. We're worried about the closest node, then the closest edge. Right? So given a node, we were always looking for this idea that we only care about the next closest edge when we already know what the next closest node is. If the node's super far away, we don't care about it. So that means you can optimize it in a greedy manner. It's very easy. You just grab the shortest thing all the time, and you'll end up optimizing globally. Yeah. So, and that's if you can wrap your head around the greedy choice property, it makes things a lot simpler. And we're going to go over how dynamic programming fits in with the greedy choice property as well. Let's start over here. Okay. So really, dynamic programming starts to pick up steam when you start to consider the nature of the optimal problem. So if we look at the optimal schedule, and this is really like the global perspective, is you want to kind of start to think globally, what does it look like? You know, with the activity selection, so given some sort of some optimal subset of A, S might look something like a continuous set of activities. And just like our bottom-up case when we're thinking about a greedy algorithm, from the top-down case we can sort of rationally start to consider what we could do with a set like this. Does anybody want to tell me what I'm about to do? If you want to consider the global problem and how you might be able to make it, what might you do with it? You might consider a slightly smaller but also large problem. So you might consider, maybe just breaking this into two pieces. And so if we use some sort of notation, like if we say that we want to talk about the subsequence, we just want to say that S star can be divided So we might have, for example, S1 to K is, these few, where this is the kth element. Then we might have S K plus 1 to, let's say, N. Which continues. But I just said we were talking about overlapping subproblems, and these don't overlap. So am I contradicting myself? Can we explain why I'm talking about subproblems that don't overlap? I just said that we're talking about overlapping subproblems.
Question, is that 1 to K, then K plus 1 to N?
Yeah. Sorry. I have the worst. So why am I talking about subproblems that are currently not overlapping, but I previously just talked about overlapping subproblems? And the answer is that these are overlapping subproblems, because we could say there's another S star quite easily, which is also in the set of optimal problems, that is actually spans from some other index J to, L, which just happens to be, so if we say this is J and this is L, happens to be in between. So it is indeed the case that we can find many overlapping subproblems. And if you subdivide them further and further, if we get down to the size of one element, then these are independent problems that can be solved and then grouped together to form, maybe these two are together, maybe they're together, Maybe these are the same elements. So if this is optimum, maybe we could reuse that solution here and here. And that's where, so it is overlapping subproblems. When we consider one optimum and divide that one optimum, we're going to find unique subproblems. But given searching the range of many subproblems, we're going to find many optimal subproblems, and we're going to be able to reuse that information over and over again. And so that's how that seeming contradiction is resolved. So that can be a sticky point when we're first thinking about these. Specifically for activity selection, let's consider this property that we're talking about as optimal substructure. And you might want to remember this, it's kind of important. And it's the idea that you can break your problems down into optimum pieces, and that conceptually you could recombine them to your optimal problem. In general, so the general idea in this case is that given you have some sort of star from some optimum from 1 to n, that J, that you can actually form your optimum solution. So that's the case. So in this case, we're using a union function. You'll see more generally, like this isn't really talked about in the course, but in general, when you're thinking about these problems, you're concerned with the idea, when you're thinking about it conceptually, as to whether or not there is a function that maps some sort of optimal thing A combined with the space of some optimal thing B to form a bigger, optimum. If that makes sense to you, it's just a general idea. So in this case, we're talking about a union, and in this course, we use a union a lot. A lot of times in stats or in information, like when we're dealing with more abstract concepts, the functions that do the mapping, when you're considering suboptimal problems or suboptimal situations and combining them to be a global optimum, you're going to be looking for some general function, and that might not mean much to you now, but in the future it might. Specifically for activity selection, let's talk about the nature of our S star. So let's consider specifically a subsequence starting at 1 to k minus 1. So we're going to have some k value as all these activities Aj to A k minus 1. And we're going to consider it as a subset of the optimals, the complete optimal solution, which is of course a subset of A. And let's consider that we sorted our activities. In here, such that why am I using the ends in the case? Actually, we'll sort the whole set, so we're going to sort this guy. So given this kth element, we should probably say that given this kth element, we'd like to look at a potential next last element. So we're at k minus 1. We're really interested in what does k look like? We want to move S1k towards the optimal solution. And dynamic programming really starts to shine when you start to consider how to form the optimal problem, because you can think of it from the top. So instead of thinking from the bottom and trying to build towards this really far away optimal objective, which you guys are seeing in assignment 1 can be quite difficult, you'll find that with dynamic programming a lot of times you'll be able to come up with a really simple formulation. If you think really hard about it, if you think about trying to build, you're given this optimal set already. You already have this optimal set. It's given to you. It's sorted, it's great, it's amazing, it's all the elements in order according to finish time. How are we going to build it one element? It turns out there's two cases, and I hope to convince you as such. The first case will be that given this item we consider at k minus 1, or sorry, at k, given this kth element, now we're going to have a situation like this. So let's say there's some AJ here. So this is not in the set actually, so make sure to be careful to exclude it in your notes. So this might be so say our algorithm is considering AJ and AJ minus 1 here. This is non-overlapping, right? There's a case where, where this item is better than this item because of the profit or the worth it has in terms of maximizing profit. The other option is quite the opposite. Given the predecessors, we're given this. So let's say actually AJ equals K. I think that's what I was going for here. So the kth element is in the set, and if we have this item is not in the set. So broadly speaking, so AJ minus 1. So essentially when we get to K, there's this idea that we can or we can't include the previous items in the set. So you might have the next item back, you might be preferred to that item. You might, even though you overlap, you should kick them out because you're a higher profit item for the weight. But it might also be the case that the item that's already there is optimal and you should definitely keep it and it's perfect and you should forget about the current item. Does that sort of make sense intuitively? So it's not just about overlap, it's about overlap and profit. And it can be hard because you kind of have to consider how the next step is going to affect the rest of the predecessors before that. And that's not an easy problem to think about. Like, what are the local conditions that lead to making that good choice? Because it also depends on how things, if you bump this item, then you're leaving a gap, right? So how does that affect the previous choice that was before it? Because maybe you could have fit something in that gap. Maybe that actually changes the whole subproblem before. So it's not a trivial, it might seem like, oh yeah, just pick the highest profit of the last two. It's not that simple, or else we would have had a greedy approach. So it turns out that the problem actually has a recursive structure. And if we really consider it, we can form this concept of a predecessor. So let's do that now.